Alright, here's an interesting problem. You have two functions, f and g, from the reals to the reals with the following property. They are continuous, and also for all q in the rationals, f of q equals g of q. And the problem is to show that the same is true for all reals. For all x in the reals, f of x equals g of x. And this seems like it makes sense because there's just so many rational numbers. There's not really any room for a continuous function to jump away. And what we're going to do is a proof by contradiction. So we're going to assume that there's some x0 such that f of x0 does not equal g of x0. And what that will do is, since f and g are continuous, that means there's some region around x0, and f will map everything in this region into a region around f of x0, like this. And likewise for g will map everything around x0 into another region around g of x0. And the key here is you can find a rational number in this interval. Okay, technically there are two intervals, one for f and one for g. But you can find a rational number, and the question is, where does it map to? F and g have to map it to the same value, since that's given as part of our problem. But it can't land in both of these shaded regions simultaneously, as long as these regions aren't overlapping. And that's where we'll get our contradiction from. Yeah, so that seems to make sense, but let's work through that more formally now. So I'm going to start by stating the assumption. Assume that there exists an x0 in the reals such that f of x0 does not equal g of x0. And then we're going to go to the definition of continuity for f and for g. In particular, continuity at the point x0. The limit as x approaches x0 of f of x equals f of x0, and the limit as x approaches x0 of g of x equals g of x0. Alright, and now let's just write out what this means in terms of deltas and epsilons. It's easy to kind of get lost in all the deltas and epsilons, so it helps to have sort of an idea of where you're going with the proof. So what does the definition say? For all epsilon greater than 0, there exists a delta greater than 0, such that when 0 is less than the distance between x and x0, less than delta, this implies that distance from f of x to f of x0 is less than epsilon. And we just need to choose an epsilon. This is true for all epsilons, so it's certainly true for a particular epsilon. So we're just going to choose an epsilon that's small enough so that the shaded regions don't overlap. And we're going to choose the same epsilon for both limits. There's no problem doing that. So I'm just going to say let epsilon equal 1/2 the distance from f of x0 to g of x0. Alright, and I'm also going to call this delta 1, since we're going to have one more. We're going to say there exists a delta 2 greater than 0, such that when 0 is less than x minus x0 less than delta 2, this implies distance from g of x to g of x0 is less than epsilon. And now we just need to choose a q, a rational number q, that satisfies these two inequalities so that we can draw these conclusions about the rational number q. And there's really no problem picking a q, since in any interval here there's going to be a rational number. So I'm going to say let q be a rational number, and q is in the interval from x0 to x0 plus the minimum of delta 1 and delta 2. And you can just compare q to the bounds of this interval to convince yourself that these two inequalities are satisfied. I'll just leave that as an exercise to the viewer. So we're choosing this rational q from this interval so that the absolute value of f of q minus f of x0 is less than epsilon, and the absolute value of g of q minus g of x0 is less than epsilon. Alright, and from here it's really just some algebraic manipulation to arrive at a contradiction. And I'll start by just adding these two inequalities together, and at the same time I'll also swap the order of this term. That will just negate it, but that's okay since it's inside an absolute value. So doing all that will give us the absolute value of f of x0 minus f of q plus the absolute value of g of q minus g of x0 is less than 2 epsilon. And by the triangle inequality, we can combine these two absolute values to get f of x0 minus f of q plus g of q minus g of x0 is less than 2 epsilon. But since q is rational, f of q equals g of q, and so these two terms cancel each other out. And we're left with the absolute value of f of x0 minus g of x0 is less than 2 epsilon. And what is this but 2 epsilon? This is the value we chose for epsilon. That implies that f of x0 minus g of x0 is 2 epsilon. So we'll just make that substitution and we'll get 2 epsilon less than 2 epsilon. And that's it. This contradiction disproves our assumption. That's the end of the proof. QED. Thanks for watching.